All right, you're going to like today's lesson on independent and dependent events, because what you're going to see is that it's really stuff you've done before. After I go through this independent events, you're going to say, I did that. Then you're going to think, I did it yesterday on the quiz, or at least if you did it correctly, you did this yesterday on the quiz. All right, independent events. Two events are independent if the result of the second event is not affected by the result of the first event. And as soon as you're done writing that down, I will give you an example that will illustrate it for you. All right, an example of two independent events that we've actually used would be flipping a coin and then rolling a number cube. When you flip that coin, is it going to any way affect how that number cube could roll? Any number that you could get on the number cube. Is it going to affect it in any way? No, if you get a heads, that doesn't mean that you could only get a 1, 2, or 3 on the number cube. So that is an example of independent events. Now, the math behind independent events should look strangely familiar. What do I have right here? A comma. What did we do before when we had a comma? What operation? We multiplied. What are we going to do now? We're going to multiply. So what you're going to do, just like you should have done yesterday, those last 3 questions on the quiz, we find their probability is 2 independent events, and then we multiply them. Now, see, you have done this before. 4-1 and 4-3. That's what you were finding, even a little bit in 4-4. You were finding 2 independent events and finding their probabilities. It's going to change a little bit, and we're going to add a little bit of vocabulary to it so you know what makes them independent. And so let's go ahead and get to that. Here's an example of independent probability. A bag contains 3 red marbles, 4 green marbles, and 5 blue marbles. 1 marble is taken at random and then replaced. This is the key term. This whole lesson is going to be about replacement. Here's why. Let's say I take a marble out of the bag, and let me show you through the magic of modern technology. There you go. There's your bag of marbles. It's like you have x-ray vision. You can see through the bag. And they're even, okay, this is where you all at least pretend to be impressed. Wow, thank you. Thank you very little. Okay. And I have all the marbles set out. But if I take a marble out on the first one, look at it, and then when I put it back, does that change anything for the second drawing? Because I put it back, has anything changed? No, there's still 12 marbles in the bag. So that's why it says, if it is then replaced. This is called with replacement. And if you have replacement, you have independent probability. You have independent events, because nothing has changed for the second drawing or the third or anything like that. Nothing has changed. There's still 12 total marbles in that bag. So we will find their probabilities independent of each other and multiply. All right. What's the probability, and this is what it's asking for, what's the probability of a red, then blue? That's what it's asking. What's the probability I choose a red on the first one? 3 out of 12. Good. Which reduces to 1 and 4. Now, since I put that marble back, how many total marbles do I have for my second choice now? 12 still. What's the probability I choose a red? A blue on this. 5 out of 12. So I'm going to go ahead and go with the reduced one and multiply that so I don't have to reduce at the end. 1 times 5 is 5. 4 times 12 is 48. So there's a 5 and 48 probability of choosing a red one, then a blue one if I put it back. That's with replacement. And with replacement, that's what tells you, that key, that term, those 2 words, that's what tells you that you have independent probability. So the bottom number should be the same when you have independent probability. We can also have it with any of those deck of card problems. A card is drawn at random from a standard deck of cards. The card is identified and then returned. So I see this phrase and I know it's with replacement. A second card is drawn. Find the probability that both cards will be black. I could go ahead and start off, couldn't I? What's going to be the bottom number for both of these? 52. Good. Right? Because it's with replacement. A deck of cards is 52 cards. I know they'll both be 52. Find the probability that both cards will be black. What are they? What's the probability? Well, how many black cards do I have here in the clubs? 13. And how many are here? Or that's spades. With the clubs right here? 13 more, right? So 26. So really, this is what? What's 26 out of 52? Half. Half times a half. So you have a 1 in 4 probability of choosing a black card. Then if you put it back, choosing another one. What do you think so far? Is this pretty much what we've done? Yeah, we have. All that probability in 4-3 and 4-4, those were all independent events. So we have done this. Here's where it gets a little bit different. Dependent events. Two events are dependent if the result of one, meaning the second one, is dependent of the first one. So the result of the second event is dependent on the first one. And there's going to be a key term we're going to look for here. It is without replacement. That's what causes the dependency, because suddenly something's going to change. If I have 12 marbles, I pull one out of the bag and keep it out, what happens to the total number of marbles? It went down. So won't the second event be dependent upon the first one? Yeah, heck yeah, it will be. The math is still the same though. Look. Comma, right? That means what operation? Multiply. Now, it says it's the probability of B given that A occurred. We're always going to assume when we're finding these probabilities that yes, we are getting A. Otherwise, if A doesn't occur, then B can't, so it's useless, right? So we're always just going to assume that yes, A happened, so we can go ahead and find for B. Now, the two examples that I have chosen are going to be the exact same marble and card problem, so we can actually compare their probabilities, because we can see that sometimes there are certain things that happen. We could also then figure out why the Ohio Lottery, the probability of choosing all those numbers, how many you have to get right? It's like 6? And then you can pick 6, right, to win the jackpot, and there's how many numbers from which to choose? So 0 to what, 70 or 0 to 66 or what? Does anybody know? I don't know. I don't play the lotto. Okay. Well, it's approximately 65, 0 to 65. And that's a lot of different combinations. The end of this chapter, I'll actually be able to show you with the last lesson on combinations on how many combinations there are for the Super Lotto. All right. Here's that same marble problem. Now, as I'm reading this, yeah, it's got the same number, 3 red, 4 green, 5 blue. One marble is taken at random from the bag. It is not replaced. So what am I going to be looking for in this lesson on all the problems? Whether by finding what words? Replaced or not replaced. That's what I'm looking for. If it is not replaced, suddenly it's dependent, right? Because what's going to happen? Your total is going to go down. It's going to go down. It's going to decrease. Right? Because what happens? How many marbles are there for the first choice? 12. I'm going to take it out and not replace it. How many are going to be there for the second one? 11. So what I'm looking for is the probability of red, then blue. That's what I'm looking for. On that first choice, what's the probability of choosing a red? 3 out of 12. Now, once I choose that red one, look what happens. How many marbles are left now? 11. You can count them. I got rid of that red one. There's only 11 left. So that's why we put the 11 down. What's the probability of choosing a blue one now? 5 out of 11. Now, before I finish this, what do you suppose happens to the probability, the overall probability, compared to that first problem? If we're taking it out and not replacing it, do you think the probability increases or decreases? Increases? Let's see. So 3/12 will be 1/4. 5 and 44, so it did increase, didn't it? Because that first time, it was 5 out of 48. So why did it increase? Yeah, because there's one fewer in the bag, right? You actually had a better chance to pick a blue one because there was that red one made the one fewer in the bag. That's correct. That was Chris Johnson. Show your dad now. Who got that right? All right. I want to show you something though, because do you think it always works that way? No, I wouldn't ask you if it didn't, right? Just why would he say something? Let's find the probability. Now this is a follow-up question of getting a red, then a blue, then another red. All right, let me go back and put my marble back in there. Okay, there, my marble's back. What's the probability of getting a red on the first one? 3 out of 12, right? There's 3 red ones, 12 total. So I go ahead and I take that red one out, keep it out. Now what's the probability of getting a blue now? 5 out of 11. So I'm going to multiply times 5 out of 11. All right, now I'm going to take that blue one out. What's the probability of getting a red one now? 2 out of 10. What happened to the number for the red? It went down too, didn't it? So what we'll see, especially with the next problem, is the probability actually decreases overall if you without replacement if you're choosing the same thing, because suddenly not only are there fewer from which to choose, but there are fewer of that kind. So this was only 2 out of 10. So all that reduces to 1 in 4 times 5 out of 11 times 1 out of 5. The 5's cross cancel, and I get 1 in 44 probability of choosing a red, then a blue, then a red. Or you could do red, red, blue. It's still going to be the same thing. The numbers just get moved around a little bit. Any questions so far? Here is where I'm going to show you that the probability actually decreases without replacement. If you're choosing different things, the probability will increase. Like if I went from black card to red card without replacement, it would go up. But since I'm looking at choosing 2 black cards, well, you'll see what happens. And once again, I know this is dependent because, see, there's that term not returned. This is without replacement. So the total number of cards is going to decrease. So on the first one, I'm going to have how many? 52. How many am I going to have on the second one? 51. All right, what's the probability of choosing a black card on the first? 26, which is a half, right? 26 out of 52. So I go ahead and just assume that, yes, I do get a black card. I take that black card away. Now, what's the probability on the second one of choosing a black card? 25 out of 51. So if it's the same thing, not only does the bottom number decrease, but so does the top number. So that's 25 out of 51, which is 25 in 102 probability. That is less than 1/4, isn't it? Because 25 out of 100 would be 1/4. So that's the probability actually decreased because I was looking to find the same thing. And if I did it again and again, black, then black, then black, each time this fraction, the second fraction, would keep getting smaller and smaller. And the probability would be getting much less because you'd have fewer black cards. There'd be more red cards from which you could choose. All right. What do you think? What's the operation we're doing today? Multiplying, yeah? All right, pages 170, 171, 1 to 25, all.